Okay, now I'm not muted. I see people trickling in. Let's give it a couple more minutes and then we will get started with lecture 11. Is this correct? This should be lecture 12, right? Somehow I have a bug on my slide, so I'm going to fix that now. This might be a bug in the uploaded slides also, so we will fix that. Okay, I think we can get started right now. I think we have quite a few people in. So welcome back from the longer Easter break. We're going to continue learning about microarchitecture in this lecture. In lecture 11, we started microarchitecture in more depth than before. And today we're going to go even deeper, continue finishing up the single cycle microarchitecture and cover multi-cycle microarchitecture. And we build up to pipelining, which we will start tomorrow. So hopefully it'll be quite exciting on all these topics. And these are the readings. This includes last time and today. Today we're going to cover multi-cycle plus single cycle. And tomorrow we'll start pipelining and continue with pipelining issues. Over the course of the next few lectures, we're essentially going to improve the performance of the basic machine that we designed last time and make it much, much more powerful, culminating in out-of-order execution, for example, and looking into deep issues in out-of-order execution. And essentially, we're going to get to very close to state-of-the-art CPUs today in terms of what they do in instruction processing to improve performance. So it's going to be a lot of fun, hopefully. We're going to tackle some really interesting issues in pipelining as well as out-of-order execution, which are not written completely over here. And then we're going to jump into other paradigms as well. Okay, so recall this is what we were doing. Essentially, we're building a basic instruction processing engine, a single cycle machine, where each instruction takes a single clock cycle to execute, and we use only combinational logic to implement instruction execution. And as a result, and there are no intermediate programmable invisible state updates. Basically, you take the architectural state, you process the instruction one clock cycle, and that produces architectural state prime. Just like what von Neumann model dictates that we should do. So we're not violating any of that. And recall, this is the instruction processing cycle. And recall, we already defined what a single cycle machine is. All 6 phases of the instruction processing cycle take a single machine clock cycle to complete. Whereas in a multi-cycle machine, that's not true. And we're going to see that today in the second half of the lecture. All 6 phases of the instruction processing cycle can take multiple machine clock cycles to complete. So you're not limited to a single long clock cycle, essentially. In fact, in a multi-cycle machine, each phase can take multiple clock cycles to complete, as we discussed, but we're going to discuss and see it in much more detail today. And recall, this is the representation of our single cycle machine. Basically, there's sequential logic registers that represent the architectural state, and combinational logic acts on it to produce architectural state prime for the next cycle, essentially. And each cycle processes an instruction. And recall, we also discussed what is data path and control logic. So this should be very clear by now. In the last lecture, we said that an instruction processing engine consists of 2 components. And if you want to design a single cycle machine, you first design the single cycle data path and add the control signals that are necessary to control that data path, and then design the control logic. Basically, these 2 components are data versus control. This also exists in other domains like networking. For example, you have a data domain and you have a control domain. That happens also in processing, as you can see. Data path consists of hardware elements that deal with and transform data signals. In contrast, control logic consists of hardware elements that determine control signals, meaning signals that specify what the data path elements should do to the data. So control enables the data path to transform the data signals. So a data path consists of functional units, hardware structures like wires, muxes, decoders, tri-state buffers that enable the flow of the data into the functional units and the registers, and storage units that store data like registers. It could also be memory as well. Control logic, on the other hand, is elements that control all of these elements. And we have seen examples of this. And last time we were building a single cycle data path for different types of instructions. I remember we actually built the data path for arithmetic and logical instructions as we were building up a simple MIPS machine. And remember, this is the data path for R-type and I-type ALU instructions. We spent a lot of time to build it, so I'm not going to cover this in detail. But what this means is that you need to add the data path elements that enable the execution of these R-type and I-type ALU instructions. And in this particular case at the bottom, I show you an I-type instruction, which is an add immediate, which essentially takes a general purpose register RS, adds to it sign extend immediate, and puts the result into a general purpose register specified by RT. And essentially, we need to have the data path components to enable the execution of this instruction. You can see, for example, that we can get one of the registers RS out of the register file. So instruction can get fetched, of course, to PC if the instruction at PC gets fetched. And instructions bits 25 through 21 specify RS. And the bottom part of the instruction, the 16 bits, specify the immediate. That gets sign extended via data path elements to 32 bits. And you can see that we enable the addition of that to the register that we read using the ID that's coming out of the instruction. And the ALU result has a way to get back into the register file through this data path wire, if you will. And clearly, to be able to execute other instructions, like R-type instructions, the ALU needs to be able to get the result second input from the register file. And you need to have a select between them. So there's a MUX multiplexer that acts as a selector between whether you have an R-type instruction reading a second register, or whether you have an I-type instruction that is acting on a sign extend immediate. So that's the purpose of this MUX. And whenever you have a multiplexer, you need to have a control signal, as you can see. And this is I-type control signal basically determines whether you read from the register or read from the, whether you operate, whether the ALU input, second ALU input comes from the register or comes from the sign extend immediate. So we already actually went through all of this, so I'm not going to go through this in detail, but just to jog your memory, we added the data path elements, and then we added the control signals, just like I showed you, to ensure that we can execute these R-type and I-type ALU instructions. So if you want to recall all of this, please watch lecture 11. Of course, ALU operation needs to be specified as well. And you just need control signals to enable register write in this case, because we're writing to the register with R-type and I-type ALU instructions. We always write to a destination register with these instructions. Okay, we also showed the data path for data movement instructions in lecture 11. And this is actually the data path for not just data movement instructions, but all non-control flow instructions. This includes the R-type and I-type instructions, plus loads and stores. And this was the data path we stopped at the end of lecture 11. Basically, this can execute R-type and I-type instructions plus loads and stores, load word and store word. And just to jog your memory, let's take a look at how a load word is executed. Load word actually happens to be the most complicated instruction in general in machines. Load instructions are the more complicated instructions because you need to actually determine the address also. So to be able to execute a load, for example, you need to have one of the source registers coming to ALU input 1 and a sign extend immediate coming into the second input. And that the ALU result gives you the address of the load, effective address of the load. So there's a question in chat. It says LDR. That's true, LDR in LC3, but LW in MIPS. So LDR in LC3 is equivalent to LW in MIPS. That's what I'm talking about. So you get the address, you calculate the address that way. So you need to ensure that is I-type is actually set to 1 so that you pick the sign extend immediate so that you can calculate the address and load word. And then if you need to set a memory read signal so that you read from memory. And then the memory provides the data. And that data needs to be written to the destination register, as you can see. So this mem to reg mux needs to be set to select this input coming from the output of memory so that output of memory gets written to the destination register, not the ALU result, as you can see. So this data path component is there to enable the ALU result to be written into the register file, but that's not used in a load word instruction because load word instruction writes the memory output to a destination register. And destination register is selected by some bits in the instruction, and load word happens to be an I-type instruction, if you remember, and that needs to select the bottom input or the top, actually, top one over here. Anyway, for more detail, look at the previous lecture, but I just imitated how a load word executes on this data path that we built last time and how the control signals need to be set. Okay, we're going to talk more about the control signals. Actually, we're going to have a lot of fun with setting the control signals once we construct the full data path that can execute a large number of instructions. But before we construct the full data path, we should talk about control flow instructions, because they're the third type of instructions that we need to place data path and control logic for, but we have not talked about them yet. We talked about operate instructions, R type, I type. We talked about data movement instructions, load word, store word. Now it's time for control flow instructions. And we're going to start with a simple control flow instruction, which is the J instruction in MIPS, jump, which is an unconditional branch or jump, as you can see. It's easy, as you can see, the semantics we already saw before. Basically, if the instruction is a jump instruction, the bottom 26 bits of the instruction are interpreted as an immediate value, and the target address of the next instruction, the next program counter, is unconditionally determined to be program counter plus 4, incremented PC, the top 4 bits of that, concatenated with the 26-bit immediate, concatenated with 2 bits at the bottom. So that's how you form the target address, essentially, by concatenating these 3 components. Program counter, immediate, and 2 0 bits at the bottom, because it's a byte addressable machine, if you remember. And the program counter should get this target address. Basically, we need to have the data path elements and the control logic to be able to execute that instruction. So let's actually add this to an earlier form of the data path that we have. So if you remember, this was our R type and load word, etc. This doesn't have all the components, but don't worry about that over here. We're going to deal with this part over here. Remember that any instruction needs to increment program counter by 4. A non-sequential, this is a sequential control flow. All of the prior instructions, non-control flow instructions, require this data path element, PC plus 4. We have an adder specially. Now we need to actually have another path to increment the program counter, because we want to be able to execute the jump instruction, right? So to be able to do that, what do we do? First of all, we need to make sure that nothing else, no harm is done in other parts of the pipeline, right? Whenever a jump is executing, we're not writing to a register. We're not reading from memory. We're not writing to memory. We should make sure that no harm is done whenever we're executing the jump instruction. Clearly, this is obvious, because jump doesn't write to a register or write to memory or read from memory. So what do you do to make sure that no harm is done? Basically, you need to ensure that register write signal is 0, meaning that we're not writing to a register. Mem write signal is 0, we're not writing to memory. And mem read signal is also 0, we're not reading from memory. I mean, mem read signal can be ignored. Potentially, you could read from memory, right? Assuming it doesn't do you any harm. So that could be omitted. And in some of the pipeline, in some of the microarchitectures in your book, for example, they omit this mem read signal. They talk about the mem read signal, but having this mem read signal to be 0 could be good, because that way you ensure that you don't access memory, which can save power, for example, save energy, right? If you don't have a mem read signal, you read memory, fine. You get some result, but you ignore it in the end. But that consumes some energy potentially. So if you have a mem read signal that's set to 0, you can save energy. But you will see in one of the other microarchitectures that we will examine quickly. But in the book that you're reading, H&H, Harris and Harris book, you don't have a mem read signal, and that's fine, because reading from memory doesn't do harm, right? It just potentially consumes more power. You could argue that that's harm, but it doesn't architecturally do harm. Basically, it doesn't clobber some value in memory. So a real harm is done when you write to registers or write to memory when you're not supposed to. That's why these control signals should be set to 0, and memory read should be set to 0 if you're not reading from memory to save power. And all of the other control signals, in this case, we don't care, because we're not really doing anything in this part of the data path. This part of the data path was constructed to execute other instructions. To be able to execute jump, we need something else in this part of the data path, which is the fetch part of the data path, if you will. And this is something else. Basically, we need another way of changing the program counter. So you can see that some bits of the instruction, bottom 26 bits, get concatenated with top 4 bits of the, actually, it should be incremented PC. There's actually something wrong over here. If you're, and I actually did intentionally, because there are actually a bunch of things wrong in this data path, as you will see. But basically, it should be incremented PC according to MIPS, and that should be concatenated. So you really need to get it from somewhere else, meaning here, if you will. And then that should be concatenated with the 26 bits at the of the immediate, and bottom 2 bits should be zeros over here, as you can see. Okay, and you need to enable another path to update the program counter. So the program counter can take PC plus 4 or the new target address that is formed by this new concatenation. And if the instruction is a jump, then you select the target address that's coming from this concatenator as opposed to PC plus 4. Okay, but as you can see, as I said, you need to be very careful with how to construct the target address. So if you go back to the instruction, we said this is the incremented PC, right? But here, the designer made an error. They did not take the incremented PC. They took the PC directly from the PC register, where we should have really taken it from PC plus 4 and put it into the concatenation logic. So this is you need to be very careful to make sure that you actually implement what the ISA, instruction set architecture, specifies. And you need to be even more careful when you implement other instructions like jump register, jump and link register, which we're going to see in a little bit. Okay, so hopefully this is clear. More jumps, more target addresses. So depending on how you form the target address, you need to increase the size of this multiplexer on this left-hand side, because there are different ways of calculating the next PC program counter with different jumps. For example, jump register. If you remember the semantics, I will show you in the next slide, but if you remember the semantics, jump register reads a register, takes the value of the register, and puts it into the program counter. Basically, it's a register mode addressing. And to enable that, you need a data path wire like this. And also, you need to widen this mux now. Basically, if it's a jump register instruction, then you need to actually select this middle input of the mux to load or update the program counter. Okay, that's true for jump and link register also, actually. But jump and link register does something else, or jump and link does something else. They basically store the incremented PC to a destination register. Okay, so basically you need to take this PC and store it into the destination register, but that's wrong again. You should not take this PC. That's not the incremented PC. You should really take the incremented PC, PC plus 4, after the output of the adder, and write it into the destination register. And the destination register ID needs to be specified by the instruction. So I'm not going through this in detail. You can actually do this in detail on your own or read your book. Your book doesn't go into this much detail also, but you can basically, once you know the specification of the instruction, you can add anything you want to the data path so that you make sure that that instruction is executed by the microarchitecture. Of course, you need to add the data path elements. You need to add the control signals as well. And these are, for your information, different ways of doing jumps in MIPS. Jump and link, as we discussed, basically, you calculate a target address gets a PC, but you also store the PC plus 4 incremented PC into a destination register. It's very similar to jump, but there's a linkage that's also provided. Jump register, as I said, you basically take a general purpose register, put it into the PC, its value into the PC. And jump and link register does this, plus stores the PC plus 4 incremented PC into a destination register so that we can do the linkage, procedure linkage. If you remember from an earlier lecture where we talked about assembly programming, these enable procedure calls easily so that you can get back to where you jumped from easily by essentially returning through this destination register that you just loaded. Okay, so clearly, if you want to implement an ISA, you need to completely implement every single instruction in your single cycle machine to make sure that your ISA actually works without any omissions in the instruction set. And to be able to do that, you need to know exactly what your ISA is. So clearly, MIPS is a big ISA. It's not a small ISA. I've given you some examples of instructions, but clearly there are other instructions like or immediate, set less than, etc. Load floating point. There's floating point instructions also. We're not going to do that. But now you know the basics. You know how to do everything, actually. You just need to follow the specification of the instruction in the ISA, add the data path elements, and add the control signals to enable the execution of the instructions, and set the control signals accordingly so that the instruction gets executed correctly and no harm is done if an instruction is not touching some parts, or some registers, for example, or memory. Okay, so hopefully now you know the methodology to really build a single cycle microarchitecture for an entire instruction set architecture. It's really not different from what we did. You just need to repeat what we did for every single instruction. Of course, while doing that, you need to think carefully in terms of, oh, should I reuse some of the hardware components that I already added for the other instructions, which is a really good idea, actually. But sometimes when you reuse the hardware components, you may have a large mux multiplexer that may or may not be a good thing, depending on the critical path, which we will discuss later on. So there are trade-offs associated with how you actually extend the basic design that I showed you to a full ISA. Okay, so conditional branch instructions is something that we did not discuss. I will briefly discuss that also because it's important to execute. Conditional branch is more complicated, especially in MIPS, as we discussed. This is a branch if equal instruction. Basically, if you remember, the semantics of this is that you calculate the target address by adding the incremented PC to a sign extended immediate, of course, multiplied by 4. Or shifted by left shifted by 2, in other words, and this target address gets put into the program counter if the general purpose register RS is equal to general purpose register RT, as specified by the instruction, as you can see over here. Okay, clearly this is we've discussed this before, and if that's not the case, if that condition doesn't hold, then PC gets PC plus 4, just like any other non-control flow instruction. So if you already have the components to do PC equals PC plus 4, we should add the component to provide this target address, as well as doing this checking. The question is, how do we do that? So let's take a look. So again, watch out. Basically, how do we calculate the target address? Basically, we're going to use another adder to calculate the target address over here. So we need to take the PC plus 4, take it from the data path. This time I'm actually warning you again, and add to it a sign extended, left shifted, immediate, which comes from the instruction, which already is used for other reasons, for other instructions. But we give it to this adder. So that's the calculation of the branch target address according to the specification of the BEQ instruction. But we also need to calculate the condition of the branch, whether we should actually use this target address or whether we should use this PC plus 4. Now we are extending the mux also, as you can see over here, PC mux. So the question is, of course, how do we calculate that condition? Well, ALU is a good place to calculate that condition because we already have RS and RT read from the ALU. In R-type instructions, if you remember, they actually have 2 register sources, and one register force comes from this place, and another register force comes from this place. And now we need to make sure that we calculate a subtraction to check whether the RS and RT are equal. And if they're equal, then this branch, the output of the ALU, or branch condition, if you will, controls the multiplexer over here. Basically, if they're equal, and if we're executing a branch equal instruction, then we should really select this target address to be placed into the program counter. The target address should really come from this new adder that we added. So that's actually what you need to execute a conditional branch, BEQ in this case. So we needed to add another adder. There was no way to actually execute this without another adder because we need to calculate PC plus 4. We need to add to it sign extended left shifted immediate. That's our target address. But at the same time, we need to check whether register RS is equal to RT. And that's what's done in the ALU over here, as you can see. Okay. So later, when we talk about multi-cycle architectures, we will see that, oh, you don't actually need this many adders, because we can do things over multiple cycles. Here, we have to do everything in a single cycle, right? We need to calculate PC plus 4. We need to add to it a sign extend immediate. And at the same time, we need to calculate the branch condition to determine what the next PC should be. And we have only a single cycle to do that. We cannot, we basically cannot break this down into multiple cycles. As a result, we have this complexity added, and we will discuss that. So there's one thing that we are going to ignore for now, and this is something that we're definitely going to ignore: delayed branch semantics. Delayed branch semantics is something that we will discuss. Basically, MIPS has this unfortunate artifact, which is the branch target address gets into the program counter not in this cycle, but in the next cycle. And we will discuss why that's the case, so that you can actually put another instruction to the pipeline without knowing the target address of the branch. But this will become more clear when we discuss pipelining. But we're going to ignore that because delayed branching is in general a bad idea. And we will discuss why it's a bad idea when we talk about branch handling in pipeline architecture. So for now, if you see delayed branch in your book, for example, or somewhere, ignore it. Okay, so putting it all together, basically, this is the machine that we just built. You were not maybe aware of it, but this is essentially what we built up. We built up the data path elements to execute many instructions. We built up the control signals. And we did not discuss how to generate the control signals, but we're going to discuss that now. So basically, actually, we can execute all of the instructions that we discussed on this machine. It's nicer here because it's actually cleaner, more cleanly displayed, but essentially it's the same as what we discussed earlier. So we're going to actually simulate the instructions that we discussed, or some of the other instructions as well, when we talk about control signals in a little bit. So we'll get back to this picture very quickly. So now let's talk about this control logic. How do we generate control signals? So we kind of discussed that, okay, this is what you need to do for control signals for a given instruction. For example, a load word needs to read from memory, but not write to memory. So now actually, you know exactly how to generate the control signals also. You can actually do it based on a combinational function, hardwired function of the instruction you're executing. And that's essentially what we're going to do. This is called hardwired control. And again, this is a single cycle machine. We're going to generate each control signal as a combinational function of the instruction that we have at hand that we're processing, which is at memory PC, as you know. So if the instructions are type, I type, or J type, it's going to be a bit different. But also there will be differences between different instructions. And we're going to consider different branches as well, as you can see over here. We're not going to fully consider different kind of jumps. You can imagine how to consider them, but they complicate the machine. And they're not really implemented, for example, here in the simple machine, just to keep it simple. Clearly, if you add 1,000 instructions in your ISA, its control logic will be more complicated also, but we want to keep it simple for instructional purposes. So we're going to consider all of these instructions that are in green over here, all R type and I type ALU, load word, store word, and branches and jump. So let's take a look at how we generate these control signals in orange color. You can see that there are actually 8 control signals, if I'm not mistaken, over here. They're single bit control signals. Well, there's also a PC source 1 and PC source 2 over here. They're control signals. So many control signals actually come from here, but some of them actually get processed based on the result coming from the data path. For example, this MUX, this multiplexer, is controlled based on whether the branch is taken and if the instruction is a branch, right? Then you actually get the target address as specified by the branch instructions, okay? So I think there is one question that is along this direction. Somehow I don't see it on this chat, but I saw it on this chat. It's really weird. I don't know why. Let me try to get to that. Okay, I don't even see it over here right now. Okay, there was some question, but my chat disappeared. Okay, if the condition is not met, so basically if the branch condition is not met, yes, you go to PC +4, essentially. Yeah, I guess the question was a direct message to me. I don't know why, but that's why I saw it over here. Okay, so we will actually see this in a little bit. So these are the 8 control signals. These are 8 control signals we actually created. If you remember regdest, for example, this is basically whether the destination register is RT or RD, whether it comes from instruction bits 20 through 16 or 15 through 11. And the equation to determine whether regdest should be asserted is essentially whether the opcode is 0 or not, okay? And this is based on examination of all the instructions. If the opcode is 0, then the destination register should be taken from, the ID of the destination register should be taken from instruction bits 15 through 11. And the component over here that we are looking at is this one, basically. This is the MUX. This is the control of this MUX. That's the regdest signal, if you will. Which destination register should you write to? And that's a function of the opcode, essentially. Okay, let's take a look at another example. I'm not going to go through all of them, but a register write is an interesting example. Clearly, it's simple. So if deasserted, you don't write to a register. If it's asserted, you write to a register. Clearly, you need to find out which instructions write to a register. And if the instructions write to a register, then you need to assert the signal. Okay, so if you go back to reg-write signal, reg-write is controlling whether you write to the destination register. So it should not be 1 if the opcode, basically, it should be 1 if the opcode is not a store word, is not branch, is not jump, and is not jump register. So we have some jump register over here also, basically. Basically, if the instruction is not writing to a register, this should be deasserted. If the instruction is writing to a register, this should be asserted. Clearly, you can design a combinational logic that looks at the opcodes and decides whether creates a single bit in combinational logic to set that bit depending on which instructions actually write to the destination register. Right? So there are a lot of other signals that I don't necessarily have time to go to, but ALU source, for example, decides whether the second ALU input comes from a general purpose register or a sign extend 16-bit immediate. And that's determined based on the opcodes that you have. If the opcode is not 0 and it's not a branch and it's not a branch not equal, then you assert this signal such that the source comes from the immediate. Otherwise, source comes from the general purpose register. And memory read and write are disabled depending on the instruction. These are easy, as you can see. Memory read is asserted if the opcode is load. Memory write is asserted if the opcode is store. And there are no other instructions, at least in our smaller set, that assert these. And PC source 1 and PC source 2 are what control these multiplexers, as you can see, PC source 1 and PC source 2. And they're determined based on whether you're executing a jump instruction or a branch instruction. So this one, PC source 2, is selecting between PC plus 4 or the target address of a branch instruction. And this other one is selecting the input of this mux, output of this first mux, or you can see this, the target address of a jump instruction. Okay. And that's how we decide basically based on the opcodes. But the PC source 2 is special. Why is it special? Because the control signal for this mux is evaluated not just based on the opcode of the instruction, but also what happens in the branch condition calculation in the ALU. So this is a control signal that's dependent on what's going on in the data path, because branch equal requires the branch condition to be calculated by the ALU first. The control of this multiplexer is dependent on what's going on in the ALU. As a result, you need to have this signal coming from the data path, not just from the opcode. Otherwise, it would not be a conditional branch. Okay, so that's why this is a bit special among all the signals that we examined. Okay, now let's have some fun. Basically, now that we know all of these signals, we can actually have some fun, basically enable and disable them based on the type of instructions that we're looking at. And we're going to look at R-type ALU instruction first. And we've already seen this actually. So basically, now we have the full data path. The execution of an R-type ALU instruction requires us to set the control signals accordingly. And this is how the control signals should be. Let's take a look. Basically, for branching, we should take PC equals PC plus 4. And we should set the control signals accordingly so that such that PC plus 4 flows into the PC. For destination register ID should be 15 through 11. We are writing to a register because it's an R-type ALU. We have 2 register sources. So the second source, second input of the ALU should come from the register file. Function should be specified by the bottom 6 bits of the instruction encoding. And we're not writing to memory. We're not reading from memory, but we're getting the ALU result sent to the register file. So we need to control this mux accurately, correctly. So basically, we're not doing any harm to memory, but we're writing to a register in this case. Okay. So you need to set the control signals to make sure you do what the instruction semantics require you to do, and you do no harm otherwise. Clearly, instruction semantics also specify you do no harm, but you need to be careful about doing no harm when you set the control signals that change the architectural state. Okay, so I-type ALU is very similar, except you select the sign extend immediate as the ALU input, second ALU input, and the destination register ID is different. So basically, let me go back. This is R-type ALU, this is I-type. R-type, I-type, R-type, I-type. And also the ALU control is determined by the opcode as opposed to the funct part of the instruction. Okay, load word, again, you can do this on your own. Load word is very similar to I-type. In fact, it's I-type as we discussed. But so compared to I-type, it looks like this basically. We need to add in the ALU to calculate the effective address. The destination register is very similar to I-type. The second input of the ALU is determined very similar to I-type, but we read from memory, and the data that's coming out to write into the destination register should be selected out from memory, as you can see through this multiplexer. Store word is very similar to load word, except it's a bit different, as you can see, right? So this is load word, the store word. So store word clearly doesn't read from memory. So if you flip the memory read and memory write signals, you don't care about the control of this mux because we're not going to write to the register. We don't care about the destination register ID because we're not going to write to the register because reg write signal has to be 0. Other than that, the calculation of the address is essentially the same as load word, as you see over here. Okay. Now, branch not taken is interesting. We don't write to a register. We don't read from memory. We don't write to memory. Do no harm. As a result, the muxes that control those are also don't cares. but we need to calculate the branch target address, as you can see. Sorry, we need to calculate the branch condition over here, as you can see. And if the condition is true, and this is a branch, then we need to select this. This is not taken. In this case, branch condition is false. So we need to select PC plus 4 to go over here. And this is not a jump, as you can see. Okay. So do no harm and make sure that you get PC plus 4 into the PC. So this is not taken. So the taken case, so clearly, as I mentioned earlier, some control signals are dependent on the processing of the data, which is the branch condition signal over here. Taken case is very similar to the previous case, except we need to choose the ALU result over here. Sorry, this should be adder result. This is a separate ALU basically to calculate the branch target address. Basically, we need to choose the branch target address calculated branch target address from this adder to go into the PC. So this is not taken branch. This is a taken branch. So you can see that they're exactly the same, except for the control of this mux, which is determined by this branch condition. Okay. So jump, we already discussed this. I'm not going to go through this, but you can see that jump does nothing over here. And you just need to make sure that the jump address directly goes into the program counter by controlling this mux and ignoring. You don't basically do anything. You don't ignore what comes out of this mux because you're actually taking this jump address calculation. Okay, so we've actually gone through all of these instructions. You can actually add more, as I said, and make this more complicated. Existing machines are more complicated, but they're also not single cycle for the reasons that we are going to discuss in a little bit. So let's talk about what is in that control box first. So basically, this control box, it says control over here, right? And we've already constructed, actually, we did hardwired control. Basically, control signals are generated combinationally based on bits in the instruction encoding. And that's essentially what we did. I actually gave you the logical equation. So if you go back over here, these are really the logical equations, Boolean equations that control each of the control signals. In this case, it's simple, clearly, because we have a simple machine, not many instructions. So that's what we did. We actually figured out how to do this combination logic. But it could also be sequential logic, meaning sequential control. Basically, you can have a memory structure that contains the control signals associated with an instruction. So this is called a control store. Using the opcode, you index the memory, and you get all of those 8 control signals that you need. And you use them later in the data path. That's perfectly fine also. So both types of control structure can actually be used in single cycle processors. But of course, the memory structure is more expensive sometimes, depending on how big the control signals are. But again, it's a trade-off depending on which one is more expensive, depending on how big things are. And you need to be careful. It's essentially choice depends on latency of each structure and how much on the critical path control signal generation is, etc. Whether you can build a memory access or small sequential access relatively quickly, etc. I'm not going to go into the sequential control right now, but we will talk about how to do sequential control in multi-cycle machines in a little bit, but we're not going to go into a lot of detail. So this is our review of the complete single cycle processor. You now actually know how to construct a single cycle processor because we did it. And hopefully it was simple. It was fun. Please study it on your own. We did the data path, we did the control signals, and we omitted some instructions clearly, but those instructions are also quite interesting, how we actually do that. So to complement, there's another single cycle MIPS processor. I'm not going to go through this in detail, but your book covers this. This is from Harris and Harris. It's essentially doing the same thing. To reinforce the concepts we've covered, I have some slides. I'm going to go through them really quickly because they do essentially the same thing, what we have done. And the end result looks like this, basically. As you can see, this is very, very similar to the processor that we designed. They omit some instructions. They don't actually have all the instructions that we covered, but I thought it was more important to cover some instructions that we covered, like multiple branches, etc., and jumps. So you can see that this is another single cycle MIPS processor with fewer instructions, but it looks essentially the same. Okay, you can see a PC branch, for example, over here. You can see a PC source mux over here. In this case, they have only one PC source because they don't implement jumps, for example. But please do the readings so that you can see. Let's go through a load very quickly. Basically, you have a fetch instruction step. You need to have the data path elements, instruction memory. So load word register read, you need to read the source operands just like we did. This is the first source operand, as you can see. And then the second source operand comes from assign extend immediate. And you need to be able to input that to the ALU, and you need to set the ALU control accordingly so that you actually get source A plus source B. And then you put the address into the memory, and then you get the data out, and the data out needs to have a data path wire to be written into the destination register, and the destination register is determined by bits 20 through 16, just like in other I-type instructions, load word, and you need to actually enable register write signal. Very similar to what we have done, as you can see. But the differences are, there's slight differences, as I mentioned. There's a write enable signal to memory, but there's no read enable signal. But we also discussed the benefits of a read enable signal earlier. And finally, your book basically shows that the next address of the instruction is determined PC plus 4, and that's essentially what we did as well. So concurrently to what's going on, you need to increment the program counter plus 4 also in a load word instruction, as you can see. Okay, so basically it's the same thing. You just need to design your data path so that you can execute the instructions at hand, and you need to design the control logic so that you can execute the instructions at hand. And again, I would recommend you to that in the book. So somebody says, is that in several clock cycles? There are several clock inputs? No, this is a single clock cycle. That clock input takes effect at basically you latch the signals at the end of the clock cycle, just like we discussed in a single cycle processor. So this does not take multiple clock cycles. This takes a single clock cycle, and you can read the book for that. Yeah, okay. So control signals are generated by the decoder in the control unit, and your book actually gives the control signals, how you generate them. And you can see how you generate them. Again, it's a combinational function of the opcode, as you can see. But of course, some control signals cannot be generated just by the opcode. You need the branch condition signal also, as we discussed. So this is your complete single cycle processor, and I would recommend you take a look at your book for more detail. I would also recommend you read the lecture slides and the backup slides. So I have some backup slides that go into more detail, show other instructions, for example, along the same lines as your book. So if those help you, I would recommend reading the backup slides as well. So this is the single cycle microarchitecture 1 we developed in the lectures. And this is single cycle microarchitecture 2 in your readings. And again, they're essentially the same. So, so why do we do it differently in the lectures? Because I wanted to actually emphasize some different things here, which doesn't get emphasized in the book enough, in my opinion. So for example, your book makes it more simple to actually look at the PC source, but actually PC source is a big bottleneck in modern systems today, because there are many ways of determining the target address of a branch. So this process is slightly more complicated than what's in your book, but fundamental principles are the same. Okay, so let's take a look at the evaluation of the single cycle microarchitecture now. Now that we've designed it, it looks beautiful, it works, but now we need to be critical. The question is this a good idea or design? I guess maybe I should get a show of hands. Who says it's a good idea or design? I don't see any hands, but maybe that's Zoom. Who says it's a bad idea? Okay, I see a lot of raised hands for a bad idea. If you were interacting, I would probably ask you why it's a bad idea. But basically, okay, maybe I should qualify this. The answer probably is it depends. It depends basically whether, and we will discuss why it depends later on, but it depends whether this is a balanced design, whether you have a good critical path, etc. But for this type of microarchitecture to work well, you usually this usually doesn't lead to a balanced design that has a good critical path, as we will see in a little bit. So when is this a good design? Let's defer the answer to this question. When is this a bad design? Let's again defer the answer to this question. And then the question is, how can we design a better microarchitecture? Basically, these are some rhetorical questions to think about. And I'm going to answer them actually in the next few slides. But think about the critical path that you have in your clock cycle time. That's now determined by the longest instruction to execute, right? Let's talk about performance analysis basics. I've already given you this earlier, but recall that execution time of a single instruction is cycles per instruction times clock cycle time, right? In a single cycle microarchitecture, cycles per instruction is always 1. But clock cycle time is going to be long, okay? Execution time of an entire program is the sum over all instructions that you're running of this value, cycles per instructions times clock cycle time. In other words, number of instructions times the average cycles per instructions times clock cycle time. We're going to revisit this later on also. So I have these slides just for your benefit. I'm not going to go through them in detail, but these essentially explain what I just said. Every program consists of a series of instructions. Each instruction needs to be executed. And instructions are realized on the hardware. Each instruction can take 1 or more clock cycles to complete, but in a single cycle machine, it takes only 1 clock cycle to complete. The question then becomes, how long is 1 clock cycle, right? And in a single cycle machine, or any machine, actually, the critical path of the combination logic determines how much time 1 cycle requires. This is clock period, and 1 over clock period is the clock frequency, how many cycles can be done in each second. Now, the problem in a single cycle machine will be this clock period. CPI is always 1, because we set it to be 1, but clock period will be very long in a single cycle machine, because you need to have all of the combinational logic to execute the worst possible instruction, longest possible instruction in one cycle. That's the reason. So that's why our program is going to be slow in a single cycle machine. And this is our formula, as I showed you earlier. You need to execute n instructions, and each instruction takes CPI cycles. In single cycle machines, 1. The clock frequency of the processor is f, which is 1 over the clock period. And you can see that this is the execution time of a program, n times CPI times t seconds. Okay, so let's take a look at the performance analysis of our single cycle design with this in mind. So every instruction takes 1 cycle to execute. This is given. CPI is equal to 1, strictly 1. That's what we said when we designed the thing. Then how long each instruction takes is determined by how long the slowest instruction takes to execute, right? So remember, we added data path elements to execute many, many instructions. Now we're going to figure out which one is the slowest instruction to execute. Even though many instructions do not need that long to execute. In fact, we will see that many, many instructions don't take very long to execute, but some instructions take very long, and some meaning loads. Whenever you need to access memory, it takes a long time. Even if you assume that it may take short, as we will do, still load instructions will take long to execute. So basically, clock cycle time of the microarchitecture is determined by how long it takes to complete the slowest instruction. And in general, in modern machines, memory access instructions, load instructions tend to be the slowest. Store instructions are easier because they don't write to a register, right? In load instruction, you need to access the memory and get the data and write it into a register. So it takes a long, many, many steps. So basically, the critical path of the design is determined by the processing time of the slowest instruction. So let's take a look at what is the slowest instruction to process. I've already given you a hint, but we need to get back to the basics to really understand this. Remember that all 6 phases of the instruction processing cycle take a single machine clock cycle to complete: fetch, decode, evaluate address, fetch operands, execute, store result. And we kind of collapsed that actually into 5 when we designed the data path. And it's instruction fetch, and then instruction decode and register operand fetch happens kind of concurrently. Not exactly, but yeah, there's some concurrency here. Execute and evaluate memory address, they happen in similar structures, the ALU. Memory operand fetch, and then store write back result. So the question is, do each of the above phases take the same time for all instructions? And let's take a look at that. And the answer will be no, basically. Some instructions will require more phases, basically. So clearly, each of the above phases will actually take the same amount for each instruction, but some instructions will require more phases. That's what I meant. So let's find the critical path in our design, basically. So of course, to find the critical path, we need to assume some latencies, right? Let's take a look at that. So what we're going to assume is that memory units are read or write takes 200 picoseconds. ALU and adders take 100 picoseconds. Register file read or write takes 50 picoseconds. And we're going to optimistically assume all other combination logic, multiplexers, wire delay, etc., is going to take 0 picoseconds. Clearly, that's not the case, but it's not going to change things much. But this is to simplify the analysis. So real analysis needs actually much more care, if you will. But this is, again, our goal is to really show you the basics of the analysis. So now you can look at which instructions take which steps. So you can see that instruction fetch, instruction decode, execute, memory, write back stages, and these are the resources that are used. And we have different types of instructions that we have actually implemented in the previous processor, this processor. R type, I type, load word, store word, branch, jump. Every instruction requires a fetch stage, so you need to pay 200 picoseconds. Some instructions do not require reading the register. Jump is an example. Everything except jump requires an ALU. Only load word and store word require memory. And only 3 types of instructions, R type, I type, and load word, need to write the register file. So if you do a simple analysis, ignore other combinational logic, this is the delay that you get. Load word is the longest. It requires all of the stages, and its delay is 600 picoseconds. Store word is a close one. It doesn't require register file right at the end, so its delay is 550. The others are far away. R type and I type ALU, they don't require this memory stage. As a result, they're 400 picoseconds. And clearly, branches are jobs are actually much shorter, as you can see. So to convince you, let's find the critical path while going through this data path and control logic. So let's take a look at how R type and I type ALU instructions operate. So for these to work, clearly you need to increment the program counter by 4. You need to go through this adder, 100 picoseconds. So this path takes 100 picoseconds. That's not the critical path. The critical path is reading the instruction from the instruction memory, reading the registers by 50 more picoseconds, executing in the ALU with 100 picoseconds, and then not reading memory, because these are not memory instructions. These are ALU instructions. but going through and writing the destination register into the register file. So that's 400 picoseconds for you for I-type and I-type ALU. Let's take a look at the culprits, which is our load word. Again, PC+4 is not on the critical path, but you need to read the instruction, read the register, calculate the address, read the memory, write the destination register. So you go through all of these data path elements, 600 picoseconds, which is the longest, as you can see. Store word, close enough, except you don't write to the register. As a result, this is 550 picoseconds. Branch taken, there are two potential critical paths. It could be not taken or not taken, but not taken critical path is the blue one. The taken critical path is the red one, as you can see. You need to read the instruction. You need to read the register. You need to registers, calculate the branch condition. That determines your multiplexer and 350 picoseconds, because we're assuming the delay of the multiplexers are 0. Of course, that's not true. The delay of the multiplexers are some finite amount of time, usually much smaller than the ALU delay and smaller than the register write delay. That's why we kind of ignore them over here. But if you really want to do a true critical path analysis, you should not ignore them. Okay. But hopefully that gives you an idea. Jump is the easiest one. You can see that the critical path goes through the determination of this multiplexer input as opposed to the data input of the multiplexer. Remember the critical path calculations we did? The delay of the multiplexer is determined by either the control input or the data input. In this case, it's the control input because you need to read the instruction to determine whether or not it's a jump, right? And that's essentially what we do over here. Okay, so that's essentially we calculate the critical path. Now let's take a look at some ponderings. I'm going to take a break after I get to a good point where we discuss the microarchitectural design principles. But basically, how does the control logic affect the critical path? I'm not going to discuss this, but can control logic be on the critical path? It can actually be on the critical path also. We did not show that over here. Historically, sometimes it's been on the critical path because the control store access has taken too long, but you should really try to make sure your control logic is not on the critical path in general, except for some potential control signals over here, like the control signal of coming from the data path, right? But this control logic should not be on the critical path, if you will, if you design it very carefully. Okay, so basically, the slowest instruction process was a load word. In fact, the real world is much worse. We're assuming memory is 200 picoseconds. In the real world, memory is much, much slower. We're kind of assuming a magic memory, right? If you remember, it's combinational memory. What if memory sometimes takes 100 milliseconds to access? That sounds terrible, right? Does it really make sense to have a simple register-to-register add or jump to take 100 milliseconds plus all else to do a memory operation? So that's the problem with a single cycle microarchitecture. Memory can take very long and everything becomes as slow as memory in this case, right? So there's one question. Isn't the control unit always part of any path since it's needed to know what path to compute? Absolutely, yes. It is true. But in the end, that gets hidden in some way. In the end, the data path computation that we saw in the load becomes the critical path. So if you look at, for example, that's a very good question, actually. For example, in the load, the critical path is this. The potential critical path is actually the multiplexer signals that come out of the control logic, but they're generated very, very quickly. The processing of that is overlapped with what's going on in the data path. Remember, this is all happening concurrently. But that's a very good question. If your control signal takes too long, you have a problem, basically. Okay, so basically, what if you need to access memory more than once to process an instruction? Then you have an even bigger problem, right? And we've seen that in load, actually. So which instructions need this? So load instruction needs this, right? Load instruction, you need to fetch the instruction first. You need to access instruction memory. And then you need to load the instruction, load the data from memory, from the effective address. That takes another memory access. And if each of them takes 100 milliseconds, then you have a big problem, right? So do you provide multiple ports to memory? I'm not going to discuss this, but we're going to get back to this when we talk about multi-cycle microarchitectures. So basically, now I'm going to deconstruct the microarchitecture that we built. There's a huge problem with single-cycle microarchitectures. And if I have to use one word to identify the problem, I would say it's complexity. Basically, this is just too complex to design. Why? It's contrived. It's inefficient. It's not necessarily the simplest way to implement an ISA. It's not easy to optimize and improve performance. So let's take a look at this. So contrived because all instructions run as slow as the slowest instruction. And this doesn't make sense if a memory access is taking much longer. Why are you slowing down every other instruction? An add can be done very quickly, right? It doesn't require memory access. Why are you slowing down all of the other instructions that don't require as many memory accesses, right? Inefficient because all instructions run as slow as the slowest instruction. you must provide the worst case combinational resources, hardware resource in parallel as required by any instruction. And you need to replicate a resource if it's needed more than once by an instruction during different parts of an instruction processing cycle. And I've shown you an example, right? For conditional branch, for example, you have an ALU, but you cannot use the ALU to compute the branch condition and also compute the branch target address if you have only a single clock cycle. You need to provide another ALU or another adder, let's say, to compute the branch target address, while you can also compute the branch condition, right? But if you can have multiple cycles to do these things, you can use the same ALU for different purposes in different clock cycles by using different control signals, right? That's the idea, basically. So this is very inefficient because you need to keep adding hardware resources so that you can do everything that's specified by an instruction in a single cycle concurrently. Okay, and it's also not the necessarily simplest way to implement ISA because there are complicated operations in ISA. For example, rep move s. We did not discuss this, and we're not going to discuss this, but this is a string copy operation x86. It's a complicated operation. You can actually copy 1 million bytes from one location in memory to another location in memory using just a single instruction, x86. I said 1 million. That's just an example, but there's a counter register that determines how many you should copy. So I can actually copy 10 million bytes. And clearly there are 10 million times 2, actually times 3 memory accesses you need to do that. Well, times 2 in this case because it's a copy. Clearly, you don't want to be doing 10 million memory accesses in one cycle, right? In fact, how do you do that? I'm not even sure how you actually can build this. So it becomes contrived very quickly. And it's also not easy to optimize and improve performance because you cannot optimize a common case. You say, oh, I have add instructions as the frequent instructions. I'm going to have to optimize add instructions or multiply instructions, whatever you want. It doesn't work because you have to, your clock cycle is determined by not them, but by a load instruction that does the accesses to memory. So you will need to optimize the worst case all the time to reduce your clock cycle time. But this is really hard, actually. This is not easy. So basically, the single cycle microarchitecture actually violates key microarchitecture design principles. We've already seen this very briefly, but these are critical path design, bread and butter, or common case design, and balanced design. Now let's take a look at what these are. Critical path design says find and decrease the maximum combinational logic delay. Break a combinational path into multiple cycles if it takes too long. And we cannot do that because we have only a single cycle. So we violate this principle. It violates the common case design principle or bread and butter principle. This dictates that you should spend time and resources on where it matters most. Improve what the machine is really executing. Common case versus uncommon case. So if the common case is you're doing 60% add instructions, you cannot do that in this case because you cannot optimize the add. Add's performance is dictated by load word, as we've seen. You have to optimize the load word. And essentially, you're violating this also. Balanced design says you balance instruction and data flow through hardware components. You design to eliminate bottlenecks, balance the hardware for the work. Again, you cannot do that by definition because you're limited by the longest instruction. And it's not a balanced design because everything is determined by how fast you can process the longest instruction. Balance requires you balance the critical path, for example. You balance the different resources. Now, you cannot balance the resources. You have to provide the worst case combinational resources, which may actually lead to bottlenecks as well. Okay, so basically, I've shown you that single cycle design violates all of these design principles: critical path design, bread and butter design, and balanced design. I'm not going to go more into detail. We don't have that much time. But I will finish up before the break with these system design principles. So we're talking about principle design, right? When designing computer systems and architecture, it's important to follow good principles. This is true for any system design, actually. Real architectures, buildings, bridges, good consumer products, mechanisms for safety and security critical systems, etc. Basically, we need to have principled designs, and single cycle designs are not good. And remember, at the beginning of this course, I said we're going to talk about principles in design. And I actually gave you this quote: architecture should be based upon principle and not upon precedent. The single cycle design are a great example of how we can break the principles. And remember, this was the precedent-based architecture, and this is the principled architecture. And remember, we compared them also, just to jog your memory. And remember, we actually discussed the slide. It all starts from the basic building blocks and design principles and knowledge of how to use, apply, and enhance them. A single cycle microarchitecture actually uses basic building blocks that we built so far. Multi-cycle will use essentially the same thing, but single cycle violates the principles essentially. Okay, I'm not going to talk about these slides, but basically, the methods used for design depend on the principles employed. But if you actually break some of the principles, you may have a bad architecture like the single cycle design. Okay, I'm going to leave you with this and then we'll take a break, but we will continue to cover key principles in this course. And here are some references where you can learn more. I'm not going to cover these. I actually mentioned this paper by Yale Pat that talks about requirements, bottlenecks, and good fortune, agents for microprocessor evolution. It introduces the levels of transformation, design point, etc. It actually talks about a lot of good principles. I recommend you to read it if you have time. Mike Flynn, we're going to talk about this later on, very high-speed computing systems. This introduces the idea of Flynn's bottleneck or balanced design principle. Gene Amdahl, Amdahl's law, probably you've seen this many times. I'm actually going to potentially assign this as an extra credit assignment later on. But this introduces the Amdahl's law and the idea of common case design. And I also recommend reading Butler-Lampson on hints for computer system design. Let me conclude with a couple of key system design principles. And a key system design principle is keep it simple. And I think the single cycle microarchitecture actually violates this keep it simple principle in a very bad way, as we discussed. I'm not going to harp on it again. And a principled person, let's say a scientist, actually has given this quote: everything should be made as simple as possible, but no simpler. Probably some of you recognize this quote. You may have seen it somewhere. Yes, that's Albert Einstein, actually, who did this quote. And it's actually true. Single cycle design actually tries to make something extremely simple, but while trying to do that, it actually violates the basic simplicity principle, if you will. And as a result, it becomes very contrived. And of course, there's other principles. Keeping it low cost is actually a good principle as well. An engineer is a person who can do for a dime what any fool can do for $1. Essentially, you can do the same thing for 1/10 the cost. And this is an anonymous quote over here. But basically, a single cycle microarchitecture violates this principle as well. As I said, you need more resources to execute every possible thing, to do every possible thing in a single cycle. So for more principles, I would recommend you take a look at Hints for Computer System Design, as well as the previous papers that I mentioned. I pick up this Hints for Computer System Design because they actually talk about simplicity and cost. And Butler-Lampson is actually a Turing Award winner for the original work that he had done to design personal computers in the 1960s. So it's a good article to take a look at. Okay, with that, I think I will ask the question, can we do better than a single cycle microarchitecture? That will bring us to multi-cycle microarchitectures. But this is a very good time to take a break. Feel free to ask any questions you may have. We'll take a 10-minute break at this point. We'll be back at 15:25, and we will discuss how we can do better with multi-cycle microarchitectures. Okay, I think it's time to continue. Can people hear me?
Yes, we can hear.
Okay, great. Okay, so let's continue. Essentially, we are done with single cycle microarchitectures and their downsides now, and we will keep asking this question that you see on your screen continuously in this course. Basically, can we do better? And this is the first. This may be the first time you see this question, but we're going to ask it more and more increasingly. In the next lecture, we'll start with this question, for example, and we will develop pipelining. But basically, you can do better compared to single cycle microarchitectures by designing multi-cycle microarchitectures. Even though conceptually this may not sound as simple, it is actually simpler conceptually, as hopefully you will see and you will be convinced of. So basically, the goal of a multi-cycle microarchitecture is what we already discussed. Let each instruction take close to only as much time as it really needs. And the key idea is to determine the clock cycle time independently of instruction processing time. Basically, you set a target. My clock cycle is going to be, I don't know, 1 picoseconds. I just made it up. Or my clock frequency should be 10 gigahertz, let's say. And I designed the machine to achieve that clock frequency. And I can break the processing of each instruction to as many clock cycles as it needs to take. Of course, I can optimize it now, but I can set the clock cycle time independently of instruction processing time. I can have multiple state transitions per instruction. So now I can have a finite state machine that dictates how an instruction gets executed, how the entire machine behaves. And that finite state machine can go through many, many different states potentially, as opposed to having only one cycle, right? It can actually go through many, many different cycles, okay, to execute a single instruction. And the states followed by each instruction is different now, meaning the control signals that are asserted in different states is going to be also different, but each instruction is going to follow different states. So basically, remember the slide. We used the slide earlier, the process instruction step. The ISA specifies abstractly what architectural state prime should be given an instruction and architectural state input, right? Basically, from an ISA point of view, there are no intermediate states between architectural state and architectural state prime during instruction execution. One state transition per instruction, but that's the ISA. But microarchitecture implements how AS is transformed to architectural state prime. And we already seen that single cycle microarchitectures look kind of like the ISA specification, basically try to execute an instruction in a single cycle, but there's no reason to do that. Basically, we can have programmer invisible state to optimize the speed of instruction execution, meaning we can have multiple state transitions per instruction. So as opposed to using the single cycle choice, architectural state gets transformed to architectural state prime in a single clock cycle, and then have all the disadvantages associated with it. We can do something like this. Architectural state gets to an intermediate state that's not visible to programmer in one clock cycle, and then to another intermediate state in the next clock cycle, and then to another intermediate state in another clock cycle. And then finally, you update the architectural state at the end of the instruction execution. So you can take multiple clock cycles to transform architectural state to architectural state prime as specified by the ISA. But whatever you do internally, you don't expose to the programmer, meaning the ISA. Everything else is microarchitectural. You don't update the architectural state clearly in between. And that's the idea over here. And clearly, you can have multiple different ways of doing this for different instructions. So one instruction can take 3 cycles. Another instruction can take 1,000 cycles if it requires to take 1,000 cycles, right? And this is important, again, because now those 2 instructions can be optimized completely independently of each other. If the common case is the instruction that takes 3 cycles, you focus on that. If the common case is the instruction that takes, I don't know, 25 cycles, you focus on that. If there are multiple common cases, you focus on both of them, as opposed to focusing on the worst case instruction, which takes lots of memory access, as we discussed earlier. Okay, so a multi-cycle microarchitecture basically does this. You have an architectural state at the beginning of an instruction. You process part of an instruction in one clock cycle, and then process part of the instruction in the next clock cycle, and then keep doing this. And then eventually, you produce architectural state prime at the end of a clock cycle. And now you can actually, it's beautiful because you can have a finite state machine that defines how you do it for every single instruction, as we will see later. And that finite state machine dictates instruction execution. And an add instruction can have, let's say, 5 states in that machine. A load instruction can take maybe 100 states, depending on the complexity of the instruction. The string copy instruction that I mentioned, that copies, I don't know, 100,000 or million bytes from one memory location to another memory location, can take 1 million cycles or longer.
a million potential states, right? Or it can stay in each state much longer to do the operations, right? Basically, you're not limited by a single clock cycle anymore. So the opportunities for optimization increases significantly. So as a result, you actually satisfy all of these key design principles. Clearly, critical path design. You can keep reducing the critical path independently of the worst case processing time of any instruction. You can say, I want a 100 gigahertz machine, and try to keep your combination logic blocks nice and clean so that you achieve that goal. You can try to achieve that goal, of course, power constraints being put aside, but you can do that. Basically, you cannot do that in a single cycle machine. You can optimize for the common case, as I said, optimize for the number of states it takes to execute important instructions or common case instructions that make up much of the execution time. If you find that out, add instructions, for example, or in machine learning, it could be floating point multiply and accumulate. You can optimize that because that could be important for your matrix multiplications. But you cannot do that in a single cycle. And it could be balanced also. Again, there's no need to provide more capability or resources than really needed in this case, meaning because you don't have to do everything specified by a complex instruction in a single cycle, you can have the minimal number of resources and reuse them over multiple cycles. And that leads to a much more balanced design that's much more cost effective. So essentially, well, I already said this, an instruction that needs resource X multiple times does not require multiple X's to be implemented. And we'll see that in the case of adders. We'll see that in case of memories. We don't necessarily need to have an instruction memory separate from data memory, for example, in this case. We can actually unify them completely because we can access memory once in one state to fetch the instruction. We can access memory again in some other state to load data from that memory, as we will see. So basically, this balanced design leads to more efficient hardware as well. You can reuse hardware components needed multiple times for an instruction. Again, all because you're not limited to a single clock cycle. You can optimize across multiple clock cycles. But of course, with every idea has benefits and downsides. And this is the key takeaway from this course, basically. You should be able to take every idea and analyze it critically in terms of the trade-offs it brings to the table. So clearly, benefits of multi-cycle design are numerous, but it doesn't come for free. It comes at a cost, actually. And the cost is you need to store the intermediate results at the end of each clock cycle. Remember the MS, microarchitectural states, as I mentioned? They don't come for free. You have to have registers to store them so that you can read them in the next clock cycle or some other clock cycle later on, right? So this increases your hardware cost. This potentially increases your complexity in terms of processing time because clearly every clock cycle has some overhead. Remember the timing and verification lecture when we said that you need to latch the data into a register? That takes time. Now you're paying that latching overhead every clock cycle many, many times, right? Whereas if your clock cycle is long, you're paying that overhead as a small fraction of the instruction execution. Now you're probably paying that overhead as a larger fraction of the instruction execution because each instruction execution takes multiple clock cycles and a fraction of the clock cycle is gone. It cannot be used because there's the sequencing overhead that we discussed for the hold time and the setup time of the registers as dictated by them. So, okay, there's hardware overhead registers and register setup and hold time overhead paid multiple times for an instruction as opposed to a single time in single cycle machines. But even despite these downsides, a multi-cycle design is much better, as we discussed, because a single cycle design is so contrived that it doesn't make sense if the instruction latencies are very wildly different from each other. So there is a regime where the single cycle design also makes sense, actually. So that's why I said it depends. And that regime is where almost all instructions, let's say, are equal in terms of the latency they take. If you can design a system like that, maybe a single cycle design makes sense. But of course, it's very hard to do that, in my opinion. By nature, instructions are very heterogeneous. A jump instruction is going to take much shorter by nature than a memory access instruction. Okay. So remember performance analysis. I actually showed this slide multiple times to you by now. So you almost know it by heart, hopefully. Execution, this is CPI times clock cycle time is cycle per instruction. That's the execution time of a single instruction, and execution time of an entire program is a sum over all instructions, or expressed this way, number of instructions time average CPI plus times clock cycle time. I already showed you the slide, actually. Single cycle microarchitecture performance and multi-cycle microarchitecture performance is very different. In single cycle, CPI is always 1, and clock cycle time is long because of the worst case latency instruction. In multi-cycle microarchitecture, CPI is different for each instruction. Average CPI is hopefully small because you can optimize for it. Clock cycle time is short as you want it to be. So in multi-cycle, basically, you can have 2 degrees of freedom to optimize independently. I said as short as you want it to be. That's not absolutely correct, clearly, right? Because you cannot make it shorter than some level. And remember the setup and hold times. Those will be the limits as to, and the clock skew that we discussed in timing verification. Those will be the limits of how short you can make your clock cycle. The sequencing overhead at some point becomes too large that most of the clock cycle time, if you reduce the clock cycle time too much, most of the clock cycle time is wasted on that sequencing overhead. And you don't want to be at that level. You really want most of your clock cycle time to be doing useful work. Okay. So recall the timing and verification lecture if you're really interested in these concepts. That's why it's so fundamental. Okay, so let's take a closer look to a multi-cycle microarchitecture and build one, essentially. I've given you the basic fundamentals, but now we're going to build one. Essentially, we're going to take our single cycle microarchitecture from your book and make it multi-cycle. But this concept actually goes back a long way. Actually, Maurice Wilks invented the notion of microprogramming, multi-cycle microarchitectures, which are a very elegant way of designing systems. I'm not going to talk about microprogramming in detail. I'm going to refer you to a lecture at the end. But you can see that this paper introduced the concept. In fact, he was quite confident in himself, as you can see in the title of the paper, the best way to design an automated calculating machine. It's a very elegant way. I don't think it's the best way in the end, because later people have shown that there are other ways, but clearly it is a very, very elegant implementation. And we're going to see parts of that implementation, but not the full thing, because there's a portion of that implementation that talks about microcoding or microprogramming, which is essentially generating the control signals and putting them into a control store memory and programming this control store, meaning programming the control signals so that you can implement any instruction that you want. That's the idea, basically, of a microprogram machines. We're not going to go into a lot of detail, but what we're going to cover is going to build toward that direction. If you're really interested, you can read this paper and watch the lecture that I'm going to talk about. Okay, so basically the key idea for realization of a multi-cycle microarchitecture is that you can implement the process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. So you remember, you have fetch instruction, you decode. Based on decode, you take multiple different states. Basically, depending on which instruction, you go to different states. But eventually, after you finish the instruction, you go back to the fetch again. And we're going to see this finite state machine later. So conceptually, this is very simple, as you can see, right? So a state is defined by the control signals asserted in it. Basically, you have a state. Fetch can take multiple states also, right? Control signals are asserted in some way, and that's the definition of your state. If two states have exactly the same control signals, they're essentially conceptually the same states. You can merge them if you really want to optimize your logic, for example, because they essentially do exactly the same thing. Control signals for the next state are determined in the current state. Basically, while you're doing processing in the data path, you also figure out what the control signals will be for your next state, if possible, because sometimes you need to get your control signals from the data path logic. But you can also break your clock cycle such that your control signals are produced in the previous cycle, and then you use them in the next cycle. So this is important so that control signals do not become your critical path. So you can actually optimize your control signals nicely if you have multiple clock cycles to optimize, essentially. So, okay, basically, this is what we were talking about. You have this instruction processing cycle. We can have many states, a finite state machine to implement this that in many, many clock cycles, depending on the instruction. Okay, so essentially, we need to divide instruction processing cycle into states. Each stage in the instruction processing cycle can take multiple states, as we already said, actually. So we're going to build a finite state machine to execute this. And you already know about finite state machines really well, except it's going to take multi-cycle. So a multi-cycle microarchitecture sequences from state to process an instruction. The behavior of the machine in a state is completely determined by the control signals in that state. I've already said this, actually. And the behavior of the entire processor is specified fully by a finite state machine. Basically, if I want to implement a multi-cycle microarchitecture specified by an ISA, I can have a, let's say, I don't know, 1,000 state machine, and that could be doing implementing the ISA. And that's my finite state machine that can, in multiple cycles, execute every single instruction in a way that specifies the ISA specification. It satisfies the ISA specification. We will see the example of the finite state machine for a subset of the MIPS ISA soon. But basically, in a state, in a clock cycle, in other words, control signals control two things. One is how the data path should process the data. And we already know this clearly, right? We said that you have data path and control logic generates the control signals to make sure data path elements do the right things to the data as specified by the ISA. But we also, in a multi-cycle microarchitecture, we can also generate the control signals for the next clock cycle. This way, while you're doing processing of the data path in one clock cycle, you're generating the control signals for the next clock cycle as well. So this way, you're overlapping, concurrently doing control and data processing. This will become a little bit more clear later. And certainly, if you do the readings, it's going to be even more clear because your readings are going to cover this a lot more than I will cover in the lecture. Okay, now let's start and design an example multi-cycle microarchitecture, the good old MIPS ISA, and implement in multiple cycles. And I'm going to use your book's implementation right now, which is very similar to what we've implemented. And again, these are very similar concepts, so you should be able to easily know what's going on. And this is an example that also has a jump actually right now. So basically, this is the single cycle MIPS processor. You can see that everything is done in a single cycle. A clock, basically, architectural state is updated in one clock cycle, and you need to have the resources to make sure that every instruction can get executed in a single clock cycle. We already discussed the downsides of it. So what are we going to achieve with a multi-cycle MIPS processor? Okay, we already said single cycle microarchitecture has low clock frequency or long clock cycle time and high hardware cost because it needs 3 adders, ALUs, and 2 memories, right? Multi-cycle microarchitecture will have higher clock frequency. Simpler instructions will take fewer clock cycles, and we're going to reuse expensive hardware across multiple cycles, as we will see. Basically, we're going to reduce the 3 adders to 1 adder and 2 memories to 1 memory. So if you go back to single cycle, this is instruction memory, this data memory, that's going to be 1. We're going to reduce these. This is a PC adder because you need to increment the PC, as you can see. This is ALU, and this is the target calculation adder for PC. Instead of having 3 adders, we're just going to have an ALU. Because we can do things in different cycles, right? We don't have to do ALU computation and PC plus 4 calculation and PC target calculation at the same time. We can do them separately in different clock cycles. Okay, so the downside is, of course, we're going to have hardware overhead for storing intermediate results and sequencing overhead paid many times across multiple clock cycles. So we're going to waste some time due to sequencing overhead, more time, let's say. But we're going to gain on the clock frequency. So multi-cycle requires the same design steps as single cycle, data path, and control logic, essentially. So we're going to do that, basically. So let's take a look at what we want to optimize, and then we're going to design the data path based on that. So single cycle microarchitecture uses 2 memories. 1 memory stores instructions, the other data. We want to use a single memory to get lower cost. Single cycle microarchitecture needs 3 adders, ALU, target PC, and branch address calculation, or PC is next PC, PC plus 4, and the branch address calculation, target PC. We want to use the ALU for all operations, again, for lower cost. Single cycle microarchitecture, each instruction takes 1 cycle, and as a result, the slowest instruction slows down every single instruction. We want to determine the clock cycle time independently of instruction processing time and set a target for ourselves as opposed to being dictated by the instructions processing time. We're going to divide each instruction into multiple clock cycles, and simpler instructions can be very fast compared to the slowest ones. And we're going to satisfy all of these requirements in the microarchitecture that we're going to build right now. So let's first construct the multi-cycle data path. So essentially, the principle of construction of a microarchitecture is always the same. You need to provide the data path based on your constraints. And here are my constraints or design goals, let's say. I'm going to put down the data path, and then I'm going to put down the control signals. And I'm going to create the control logic, meaning finite state machine. And I'm going to associate the control signals with each state based on that. That's the idea, basically. So let's start. Let's start with the load word instruction. Load word is an interesting instruction, clearly, and that was the culprit for single cycle. And this is the MIPS instruction, as you can see, base plus offset addressing and writes to a destination register. Basically, we need to read from the instruction, read the instruction from memory, read the source register from the register array, add the immediate value to calculate the memory address, read the content of this address, write to the register this content. Clearly, things that we have already done in a single cycle. But now we're going to take multiple cycles. So let's take a look at the difference. So multi-cycle data path. This is instruction fetch. Very similar to single cycle data path. you take the program counter out of the PC register, put it into the address port of instruction/data memory in this case. We're not going to write to the memory, right? Enable will be 0, but ignore that for now. Do no harm still applies clearly. The read port provides us the instruction. What are we going to do? We're going to latch it into a register. Why? Because this is our clock cycle. We want the clock cycle to be no longer than this, let's say. Now we latch it. We don't need to do anything else for this instruction. Now the instruction is going to be processed in the next cycle, be decoded, and read the register file in the next cycle. So a fetch instruction in this case takes 1 cycle, as you can see. It could have taken multiple cycles also. We could actually say this takes multiple cycles, and we will see that later on toward the end. But in this case, it takes 1 cycle, as you can see. Okay, that's beautiful, right? We're not constrained anymore. So the cost, of course, is the register that we've added so that we can latch the intermediate result. Clearly, this result is not changing the program counter, of course. It's clear this is a microarchitectural register, basically. And we have a control signal IR right for this. We're going to see the need for that later on. Okay, so basically, fetch state is the same for all instructions. Clearly, we're processing load word over here, but the other stages will be different. So in the next clock cycle, we're going to use the data inside this IR instruction register, let's say, and use it to ID the register we're reading, access the register file, get the data out, latch it. That's our clock cycle again. Somehow we determine the clock cycle and we say we latch it at this point. In the next clock cycle, we're going to just read the register. Okay? And this is microarchitectural state 2, if you will. Okay. Concurrently, you take the bottom 16 bits of the instruction, sign extend it, and this is going to be input to the ALU later on because remember, load word calculates the address by taking the base register output and sign extend immediate. Okay, so concurrently, we're going to supply this value over here. So this could also be latched or not latched. We're going to think about that later on. In this case, it doesn't need to be latched because of the way it's designed, but you could also latch it over here. Okay, we're going to see more of this later when we talk about pipelining, but in this case, this is correct that it's not latched, but it can be latched also. Okay, so in the next cycle, what happens is, next cycle essentially is the third cycle. We calculate the address, taking the value inside this register, putting it to the ALU, taking the sign extend immediate, put it in the ALU. ALU control needs to be specified accordingly, and ALU result gets latched again. That's the end of the cycle. Okay. And then the next cycle takes the result from the ALU out, this register that we added, puts it into the memory. To be able to do that, you need to add a mux to memory because now the memory is used as both instruction. Not puts it into memory. This is the address. This is the effective address that we generated. Still, it's the ALU output. This is the address of the memory location that we want to read. It gets put into the address port. But clearly, we're using a single memory, so we're going to distinguish whether we're reading an instruction or data based on where the address is coming from, ALU or PC. In this case, it's data. And essentially, the memory gets the address, and then it reads the data, outputs it into a register. You can call this a memory data register, if you will, and latch it. That's one clock cycle. Okay. In the next clock cycle of execution, we take the data that was output from memory and latched, and write it into the destination register as specified by the instruction that's still sitting in the instruction register. Remember, we're not clobbering this instruction register because we fetch the instruction. Over multiple cycles, we do stuff, but that instruction register doesn't get updated because we didn't fetch any new instruction. Okay, so we use the same control signals, the value that's in the instruction register to determine the destination register. And whether we need to write to a register right over here also, okay? Basically, these control signals can be determined before in the previous clock cycle and can be latched, or they can be determined in the same clock cycle also, okay? And we're done basically with load word. Last cycle, we wrote the data into the register file, and that's the end. Of course, that's not the end. We need to also increment the PC, but this doesn't have to be in the last clock cycle. This can be done concurrently with everything else, as long as the resource is not needed. So whenever the load word is not using the ALU, we can use the to calculate the address, which means that whenever we're not in this cycle, we can also increment the PC. And that requires taking the PC, inputting the ALU, adding the right data path elements clearly to be able to do that, inputting a 4 into the second input of the ALU so that we can calculate PC plus 4, setting the ALU control to be add, okay, and then getting the result and putting it into the PC register. So clearly you can do this at any clock cycle except for the clock cycle when we're calculating the ALU address, because in that clock cycle, ALU is being used, okay? So it's beautiful, right? Well, of course, there's overhead. The overhead, we're using ALU, reusing ALU in different clock cycles for different purposes, incrementing the PC versus calculating the address. But we need to supply the right inputs to the ALU, both to the top source and the bottom source, or source A and source B. And you can see that the multiplexers are getting wider and wider. And there are reasons for this multiplexer to be wider because it's going to be used for other instructions as well. I'm going to show that in a little bit. But this is the load word execution. We're done with load word, basically. We've done it in multiple cycles, and we've added the data path elements required for that. For store word, basically, whenever we are writing data to memory, after we latch the second register, we write it back to, we need to provide the path so that we can write to the data memory, or the memory in general, and we need to assert the memory write signals. So the control signals are actually very similar to single cycle control signals. We need to add some more control signals for the new elements we add, or to ensure that we can actually do multiple things at the same time, or use the same memory for different purposes, or use the ALU for different purposes. But control signals in general are very similar to the single cycle control signals. And data path elements are also very similar, but they're more simplified, as you can see. So store word is easier, right? It's very similar to load word, except the last step of store word is taking the output of the register file that's latched and writing it back over here to the data memory. Of course, the address needs to be calculated correctly also. Okay, let's take a look at R-type instructions. Again, R-type instructions are, again, very similar. We could execute them in this data path using multiple cycles. We need to add the data path elements, as you can see. These are very similar data path elements that we added in a single cycle. I'm not going to go through them again, but the reasons of them are also similar, because the destination register data can come from memory or the ALU, as you can see over here. And again, the destination register can be specified by different parts of the instruction depending on the encoding on the instruction. So there's a question: what's the difference between RD1 and RD2? Why can't we use a single read port? That's a very good question, actually. You can actually, in a multi-cycle microarchitecture, you can use a single read port and read different registers that you need in consecutive clock cycles. So your point is actually absolutely correct. You can use multiple clock cycles to read different registers. But in this case, we decided to use 2 read ports to simplify microarchitecture. So that if you are really hardware constrained, you can do what you suggest, basically. You can have a single read port to the register file and read different registers across multiple cycles. But usually that increases the number of clock cycles that you need to execute R-type operations, for example. That's essentially why this design choice is made. But absolutely, that could be a design choice to make. A single read port could be another design choice to make. And that can be enabled, again, by a multi-cycle microarchitecture. Very good. Okay, so this R-type. Branch equal is very similar, again, to a single cycle microarchitecture, except you need to add the data path elements. And again, branch equal executes over multiple cycles. I'm not showing the multiple cycles components. I'm adding the data path elements. But the key takeaway here is data path elements are actually quite similar to single cycle, except they're simpler. And it can even simplify more, as your fellow colleague, student mentioned, right? You can actually have a single port to the register file and do a read over multiple cycles of different registers. But basically, the control signals are also very similar to a single cycle, give or take some that you need to add for the design point that we're trying to create over here. And this is our complete multi-cycle processor. As you can see, it's very similar to the single cycle, except we have these intermediate registers, right? This is the instruction register. This is the data register, memory data register, if you will. This is the output of the register file reads that we have done. This is the ALU result register. So you can see that we've added a bunch of sequential elements so that we can do things in multiple clock cycles as opposed to single clock cycle. Okay, now let's construct the multi-cycle control logic. That was the data path. We need the control logic. And this is our control unit. So basically, we have a finite state machine that's dictated by opcode, but also other things. And this main controller will generate some control signals. Some of them are multiplexer selects. Some of them are register enable or memory enable signals, as you can see. And some of them are instruction register, for example, whether we write to the instruction register, whether we write to memory, whether we write to program counter, whether we actually, this is branch, it's not a register enable exactly, but a register write, whether we write to a register as well. And some of the control signals will determine the functionality of the ALU. So control signals are, again, very similar, but we're going to do the control through a finite state machine that sequences through multiple cycles. So the first, essentially, we're going to construct that finite state machine. We're not going to go into every single state since we don't have time, but what we're going to do is start with fetch. So fetch state is the first state that we need to execute in every instruction. At the reset, you go to the fetch state clearly. And basically, in this state, what we need to do is we need to ensure that the PC gets input to the instruction data memory. So I or D should be 0. And we don't write to memory. Do no harm. Remember, do no harm is very important. So all of the control signals that write to register, write to memory should be 0. In this case, clearly in the fetch state, we don't write to registers or memory. And whatever we read using the PC from memory should be latched into the IR write. So IR write should be 1 also. So these are the signals, basically, as you can see, for the fetch state. Again, not all of them. The most important ones are essentially, it also increments the PC. In this case, that's why we have PC write. Well, I actually didn't mention that. Basically, in the fetch state, we also increment the PC in this finite state machine. So we enable PC write, and PC also needs to get PC plus 4, which means that we should really select this source. That's why ALU source A should be 0. ALU source B should be this 4, PC plus 4. And ALU operation should be add, which is, I think, 0, 1, 0 over here, 0, 0 over here. That's how it's specified. And we need to be able to select the PC output correctly over here. So I think I've said all the control signals. Basically, we need to be able to read from memory and also increment the PC. And these are the control signals that are needed to be able to do that. And this is the idea of microprogramming, essentially. Each state is microprogrammed by setting the control signals accordingly. Okay. Now we fetch. At the end of the state, we fetch the instruction. The next stage is decode. There's an unconditional state transition. Assuming this takes 1 cycle, there's an unconditional state transition to decode. If this doesn't take 1 cycle, you stay in the state for some time, but you need to be careful about what you do over here because you don't want to increment the PC many, many times, clearly, right? So, but assume that it takes 1 cycle. The next transition is the decode state. So the decode state, essentially, you take the instruction register and input to the control unit so that you get the, you figure out what the instruction is. And for the decode state, I'm not going to go into a lot of detail as to what you should do, but you don't do any harm. First of all, you should not do any harm. You should not increment the PC. You can see that the signals are set accordingly for the decode. A lot of them are don't care, but you should not write to register file. You should not write to instruction data memory. Those are important. You should not write to PC. You should not write to instruction register. And I think those are the right enable signals that we should not set. A lot of the other things are don't cares, basically, because we're just generating the decode signals. Okay. And the writing to the latch over here, the register over here at the end of the register file is done automatically. Okay. So the next stage is more important. Basically, after decode, depending on the instruction, you go to a different state. So if the opcode is load word or store word, you go to the memory address calculation state. Okay. If the opcode is something else, we're going to add some other state. And we're going to branch out basically after decode. So let's take a look at this. So if the opcode is load word or store word, we calculate the memory address and we set the control signals accordingly so that we can calculate the memory address. And everything else, do no harm. We don't increment the PC, this is 0. We don't write to instruction data memory, write enable 0. We don't write to instruction registers, that's 0. We don't write to register, that's 0. We just calculate the memory address in this cycle using this data over here and this data over here and writing the result into this register at the end. That's our cycle, basically. So we need to set the control signals accordingly to accomplish that. And you can see that ALU source A should be 1. ALU source B should be 1, 0. It should take the sign extend immediate. It should do an addition of that, and the result needs to be stored. Okay, basically, I already said this. Okay, that's load word or store word first clock cycle. Next clock cycle, if it's a load word, we basically need to put the ALU result into the instruction and data memory. I'm not showing you at this point because that will take a very long time, but I can show you the machine, finite state machine diagram. That's the next clock cycle. Basically, you read the memory, sorry, not write the data. ALU result is used as an address to index the memory, and it's data now, and you get the data. And then you transition to the next clock cycle. In the next clock cycle, the data coming out of the memory, mem to reg is 1, is written into the register, reg write signal is asserted, and reg destination mux is selected by the 0 signal over here so that you write to the correct destination register. So this is the execution of load word. At the end of the state, you go back to the fetch. So basically, you need to have a sequencing logic, meaning next state logic. And you know how to construct the next state logic, right? You know how to construct a finite state machine right now, because we did construct the next state logic. You need to also have next state logic that determines, that takes you to the next state such that you assert the control signals accordingly after the load word is done. So this was load word. So remember what we did. We fetched the instruction, and there's control signals associated with fetching the instruction. And the state is defined by those control signals. We unconditionally transferred to the next state, which is the decode state. We did something. And then we transferred conditionally, whether the opcode is load word or store word, to the memory address calculation state, because that's the common state for load word and store word. And then if the output operation is load word, we do a memory read state. And then we unconditionally transfer to memory write back state. And then after that 1 clock cycle, we unconditionally transfer to fetch. Okay, what happened here? To store word, well, after the memory address calculation, if the operation is store word, you go to a mem write state and assert different control signals clearly, right? Obviously. And you can look at by yourself. And you can see that after that, the transition is unconditional to the fetch state again. So all of this is dictated by a finite state machine that implements the next state logic accordingly and carefully. Okay, now you can actually do the R-type instructions. You can see that R-type after decode goes to an execute state. Control signals are set such that you do the execution of the instruction. And then 1 clock cycle, in the next clock cycle, you write back the result that is latched in the ALU result into the register. Okay. And then if the operation is a BEQ, you have one state that determines the destination, basically what needs to happen to the PC at the end. Okay. Okay, this is the complete multi-cycle controller finite state machine for these operations. You can see that here, load word again takes longer, 1, 2, 3, 4, 5 clock cycles. And a BEQ takes 3 clock cycles. An R-type operation takes 1, 2, 3, 4 clock cycles. Different operations take different clock cycles. Now you can optimize different operations differently and also try to minimize the clock cycle time by balancing different combinational paths between each other. Okay, if you want to do more, if you want to add more instructions, it's easy now. After the decode state here, basically you can transfer to some other state, right? Add I, you execute add I. Again, I'm not showing you what you should do over here. You can clearly set your control signals such that you can execute the add instruction and write back in different clock cycles and do it accordingly. And the key is you need to be able to have the data path elements to execute the instruction. You need to set the control signals accordingly, and you should do no harm. You should do only the things that you're supposed to do in that state. And again, as a designer, you have a lot of choice over here. Okay, you can read for more detail your paper, not the paper, the book, as I mentioned. And you can add jump also. You can see that jump is added this way. So if you want to add a new functionality, you need to add the data path elements. As you can see over here, we're adding jump over here. What jump does is it calculates the address through the ALU, as we discussed. We don't want to use another adder. ALU result gets latched, and that ALU result can be put into the PC, or a sign extended immediate can be put into the PC. So if it's a jump, that sign extended immediate is selected by this mux. Okay. So you need to add the data path elements. You need to add the control signals. These are the new data path elements and control signals that are added if you want to extend the machine with a jump. And you need to add the state machine states. So if the opposite jump, you do the jump, and you need to set the control signals accordingly, as you can see. And if you actually change something in some other state, you need to actually set that accordingly as well. So you can see that the addition of this state actually affects control signals in other states also, as expected, because that is actually essentially you widen one mux. So let me go back actually to this. So we're almost done, but basically what I've shown you over here, we've kind of widened this mux multiplexer over here. That's why you need to change. If you want to add another instruction, you need to add states, but you may also need to change the essentially the control signals in other states. And microprogramming, what is microprogramming? Microprogramming is essentially constructing this finite state machine and writing the control signals. So you can actually have the same machine do different things by actually adding different states into the machine and setting the control signals in appropriate ways. For example, you can execute a load 1 million times, right? By doing some microprogramming and adding maybe some logic so that you can do 1 million loads at the same time. It's very powerful. Basically, you add a loop to this, and you are able to actually do that relatively easily if you have a finite state machine that's extensible like this. I'm not going to go into the details of it. I'm going to refer you to some other lecture for this. But essentially, this was our single cycle MIPS processor, and this was our single cycle MIPS FSM, finite state machine. Basically, this was our finite state machine. We have just this. Now, contrast this with our multi-cycle MIPS processor. Data path looks similar, right? This is a single cycle data path. This is a multi-cycle data path. There are some differences, clearly, intermediate states, for example, and some more signals. There are fewer memories and fewer adders in the multi-cycle. But what's really different is the finite state machine. So if you look at the single cycle finite state machine, it's single cycles. This finite state machine is completely different, right? You actually go through many different states over here, not just one cycle. And different states are determined by different instructions. Now you can optimize each state, how long each state takes. You can break one state to multiple different states, increase your clock frequency or reduce your clock cycle time. You can figure out a better way of executing the instructions by having it go through fewer states. So you can see, I think there's one question. What is the bottleneck for the cycle time in the multi-cycle system, this system? Basically, the answer is your creativity and careful engineering is the bottleneck in the end. And also some physical limits like register setup and hold time and the sequencing overhead. You can basically set your clock cycle time to as large as you want it to be within your design point and goals and try to achieve that goal by changing your finite state machine, essentially. Okay, so we're at the end, but I will also always ask you the question, what is the shortcoming of this design? This is important for what does this design assume about memory? So that's one shortcoming, for example. But there are other shortcomings. So basically, in one state, you're doing one thing and nothing else, right? Only a very small fraction of the machine is busy in this case. That was true for single cycle also, but here also. Basically, you're not really exploiting the large concurrency that's available in the machine, and we're going to fix that in the next lecture. But there's another shortcoming. Well, we will talk about other shortcomings in the next lecture also, but keep that in mind. We're using a very small fraction of the machine in every single clock cycle. We could do some things concurrently as well, potentially, and we will see what those are. This design assumes the memory is a single cycle. What if memory takes one cycle? I would recommend you to think about it. Basically, if this is the case, you need to stay in the memory access state until memory returns the data. And this is beautifully done and easily done in a finite state machine. Basically, finite state machine takes as input a ready signal from memory. Memory ready signal, it's an input to the control logic that determines the next state. And if memory is not ready, you keep accessing the memory and waiting. Of course, you should do no other harm, right? And that's the idea. And this is relatively easy to do, as you will see in the recommended reading that I will provide in the next minutes, let's say. So basically, we have built multi-cycle microarchitectures. There's more to cover here. We don't have time to cover. I'd recommend looking into certainly this paper. But for your own study, we also have in the backup slides and on the website, another microprogrammed LC3 machine that operates similarly, very, very similar to the principles that I described, except it has a different structure for the control. It's microprogrammed control, if you will. And if you really want to know what that is, you can look at these slides. Plus, if you're really interested, you can look at an older version of this class where you used to cover microprogramming in more detail, but we're not covering it this semester. If you really want to know it, you can certainly watch those lectures. And I would recommend, if you're really interested, curious, this is a beautiful way of designing machines. I'd recommend looking into it. And certainly you can find other lectures online as well. So that brings me to the end. So if there are any burning questions, I'm happy to take them. If not, I would recommend you think about how can we do better? Basically, the next question I will ask you in the beginning of tomorrow's lecture is, can we do better than this? And the answer will be yes. Of course, it will come with trade-offs, but it's going to improve our performance significantly compared to what we have done in this lecture. And there's a bug in this lecture also over here. That should be lecture 12, if you will. Okay, I think there were quite a few questions, and those were actually quite good questions as well. If there's nothing burning, I will stop here. And I look forward to seeing you tomorrow to introduce pipelining, which is going to be the way of doing better. Okay, take care and see you tomorrow.